Hello students, welcome to AIMS India online classes. This is a chemistry session. Here we are discussing about the chapter chemical bonding. In this session we are going to say a new concept, that is hybridization. What is hybridization? How many kinds of hybridations are existing? And let us see some of those types in this session. Okay. In order to explain the characteristic geometrical shapes of polyatomic molecules like methane, CH4, ammonia, and water, etc., Pauling introduced the concept of hybridization. So, to explain these structures, geometrical shapes of these polyatomic molecules in clear, scientist Pauling introduced the concept of hybridization. According to him, the atomic orbitals combine to form new set of equivalent orbitals, which are known as hybrid orbitals. And that concept or that phenomenon by in which atomic orbitals are intermixing each other to form equal energetic new orbitals is called hybridization. And those newly formed hybridized orbitals are having equal energy. So now hybridization can be defined as the process of intermixing of the orbitals of slightly different energies so as to redistribute their energies, resulting in the formation of new set of orbitals of equivalent energies and even equal shapes. That phenomenon is called hybridization, and those newly formed orbitals are called hybrid orbitals. Okay, so what is meant by hybridization? The intermixing of two or more orbitals of same atom which are having same energy or nearly equal energy. They intermix each other and they result in the formation of new orbitals, same number of new orbitals with the same energy, or is called as hybridization, and those newly formed same energetic orbitals are called as hybrid orbitals. Okay. Now let us see the silent features of this hybridization phenomenon. The main features are like this. The number of hybrid orbitals is equal to the number of atomic orbitals that are getting hybridization. Means how many orbitals of an atom are participating in the hybridization, which are going to be intermixed. The same number of hybrid orbitals will be formed. Suppose two orbitals are intermixing to form hybridized orbitals. Then the number of hybrid orbitals formed also will be 2. That means the number of hybrid orbitals formed with equal energy will be equal to the number of orbitals intermixing in the process of hybridization. Okay. The hybridized orbitals are always equivalent in energy and shape also. So before intermixing, the atomic orbitals of an atom may have same energy or nearly equal energy, and they may have different shapes. But once they are intermixed for the formation of hybrid orbitals, then the resultant hybrid orbitals will be having equal and exact equal energy and even same shape also. Equivalent energy and shape they will be having. So before the intermixing, they may have different energies slightly and they may have different shapes also. But once they intermix, then the resultant hybrid orbitals will be having equivalent energy and shape. The hybrid orbitals are more effective in forming stable bonds than pure atomic orbitals. Okay, the bonds formed by these hybridized orbitals are more stronger than the chemical bonds formed by normal atomic orbitals, pure atomic orbitals. So they form strong bonds. Hybrid orbitals form strong bonds than the pure atomic orbitals. These hybrid orbitals are directed in space in some preferred direction to have minimum repulsion between the electron pairs, and thus a stable arrangement they form. Therefore, the type of hybridization indicates the geometry of the molecule. So based upon this repulsion concept, which we have studied earlier once in the Weschmer theory, isn't it? These hybrid orbitals also, they will be directed in the space around the central atom in the preferred direction, where they will get minimum repulsion from the remaining electron pairs, and thus they form a stable arrangement. From this concept, the type based upon the type of hybridization, we can predict the geometry of the molecules. Okay. Now let us see the important conditions for the hybridization in an atom. One, it is the orbitals present in the valence shell of the atom, they are hybridized. Only the orbitals present in the valence shell, that means in the outermost shell, only they participate in intermixing, and thus they result in the formation of hybridized orbitals. Another point is the orbitals undergoing hybridization should have almost equal energy. So the orbitals which are going to intermix, they should have nearly same energy, almost they should have equal energy. That means the orbitals present in the same shell, generally they participate in the hybridization, and they result in formation of hybridized orbitals with exact equal energy. And another point is promotion of electron is not essential condition prior to hybridization. So it is not compulsory always the promotion of electron, that is the excitation of electrons is not compulsory in the hybridization. It may or may not be happened before the hybridization. In some atoms, before hybridization, electrons may excite and hence they participate in the hybridization. In some atoms, this excitation may not happen before hybridization. That means promotion of electron is not essential condition in prior to hybridization. Another point is it is not necessary that only half-filled orbitals participate in hybridization. We cannot say only half-filled orbitals they participate in the hybridization. It is not necessary. In some cases, even completely filled atomic orbitals also, means the orbitals, the paired electrons also, they may participate in the hybridization. The only condition is those orbitals should be in the valence shell. So if those orbitals are in the valence shell, they may participate in the hybridization. Even they are with the single electron or with the paired electrons. They may have any condition. There is no necessity to be with the only single electron. Okay, completely filled atomic orbitals also, they may participate in the hybridization. But that should be in the valence shell. Now let us see the different kinds of hybridization, that is types of hybridization. So based upon the types of atomic orbitals which are involving in the intermixing, the hybridization can be classified into different types. They are sp hybridization, sp2 hybridization, sp3 hybridization, and even sp3d hybridization and sp3d2 hybridization. So these are the different kinds of hybridizations. This classification is just based upon the type of atomic orbitals participating in the intermixing. So the orbitals present in the valence shell of an atom, they participate in hybridization. Based upon the type of orbital intermixing there, the resultant hybridization will be different. Okay, there are different kinds. Now let us see one by one these now in detail. First let us go through the sp hybridization. So the intermixing of one s orbital and one p orbital to give two equivalent hybridized orbitals is known as sp hybridization, and those resultant hybrid orbitals are called sp hybrid orbitals. Okay, how it is formed? By the intermixing of one s orbital and one p orbital results in the formation of two equivalent hybrid orbitals. This phenomenon is called sp hybridization because one s orbital, one p orbital, they are participating in the intermixing. That is why this phenomenon is called sp hybridization. And those resultant two equal energetic orbitals are called sp hybridized orbitals. Okay, in the name itself it is there. which orbitals are intermixing in the formation of hybrid orbitals. So one s orbital and one p orbital, they are intermixing each other to form new equienergetic two hybridized orbitals, which we call them as sp hybridized orbitals. Okay, this phenomenon is sp hybridization. Now, the two sp hybrid orbitals have linear shape with a bond angle 180 degrees. So they, in the space, as we told, these two are atomic orbitals, newly formed hybrid orbitals will be having unpaired electrons in them. So they will try to maintain maximum distance from one to another, and hence they come into linear shape in the space in the opposite directions. And hence the bond angle will be here 180 degrees. So we can say this shape as linear shape. Okay, in the sp hybridization, the molecule acquires linear shape with bond angle 180 degrees, right? In this way, two sp hybrid orbitals will attain linear shape. And here, each sp hybrid orbital has 50% s character and 50% p character. So the orbital character can be determined by using a formula, that is percentage character of an orbital is equal to the number of orbitals such kind participating in the hybridization divided by total number of orbitals participating in the hybridization into 100. This gives percentage character of particular orbital. Suppose now we are calculating here the S character, the percentage S character in this sp hybridization. If we calculate number of s orbitals participating in this hybridization. How many s orbitals are participating in the sp hybridization? Only one s orbital divided by total number of orbitals intermixing here. We know one s orbital and one p orbital, they are intermixing. So totally two orbitals are intermixing each other. Now the number of s orbitals in the numerator divided by the number of total orbitals which are intermixing, all kinds of orbitals participating, that is 2 here. So if we calculate this, we get it as 50%. So the percentage of s character in this sp hybridized orbitals is 50%. In the same way, we can calculate p character also. In this sp hybrid orbitals, the p character, if we calculate, p character is equal to number of p orbitals participating 1 divided by total number of orbitals intermixing is 2 into 100. There also we get 50%. That means s character is 50%, p character is 50% in this sp hybridized orbitals. Okay. Now sp hybridization is also called as diagonal hybridization. Okay. Now, let us see some example for the molecules having this sp hybridization. To explain this, let us consider the formation of BeF2, beryllium fluoride molecule formation. Let us consider to understand this sp hybridization. We know in the beryllium fluoride BeF2 molecule, the central atom is beryllium. So the electronic configuration of beryllium is because atomic number of beryllium is 4 and its configuration will be 1s2 2s2, and the electron configuration of beryllium in its excited state is, means one electron jumps from s orbital to p orbital in the second shell. Then its excited electron configuration will be 1s2 2s1 2px1, means there are two electrons in the unpaired position. Two orbitals are there with unpaired electrons, 2s orbital and 2px orbital. Okay. Now in the excited state beryllium atom, 2s orbital and 2px orbital intermix each other to give two equivalent sp hybridized orbitals. So actually the shape of s orbital will be spherical and the 2px orbital is having dumbbell shape. But once they are intermixing each other, two equal energetic equivalent hybrid orbitals are formed which are having same shape. Those new orbitals formed here are called sp hybridized orbitals. Sp hybrid orbitals also you can say. These will be having equal energy as well as equivalent shape also. Initially, if you see 2s orbital is having slightly less energy than 2p orbital, isn't it? And even the shape also is different for both. But once they are intermixed each other, the resultant orbitals are having equivalent energy as well as a shape. Those are called sp hybrid orbitals. Now, each sp hybrid orbital will be having these unpaired electrons, one in each. This will be having one unpaired electron. This will be having one more unpaired electron. Just like these pure orbitals, pure atomic orbitals, how they are having single electrons. Once the formed hybrid orbitals also will be having single electrons in them. And in the other way, if you see the electron configuration of fluorine atom, we know atomic number of fluorine is 9 and its configuration is 1s2, 2s2, 2p7. So to say in clear, in the 2p subshell, the configuration will be like this: 2px2, 2py1 and 2pz1. Means fluorine has one half-filled p orbital, that is 2pz orbital, isn't it? The half-filled 2pz orbital of two fluorine atoms overlap with the sp hybrid orbitals of beryllium atom in their axis to form two sigma bonds. See here, beryllium, it already undergone a hybridization and formed two sp hybridized orbitals. Each one has unpaired electron. And 2p-z orbital of each fluorine. They approach to the beryllium and they overlap with the sp hybridized orbital of beryllium. So it occurs here spp overlapping, and thus they form a sigma bond, that is called spp sigma bond. Here also spp overlapping is occurring, and thus they are resulting in the formation of a sigma bond. So in that way, beryllium difluoride molecule is having two sigma bonds which are formed by the spp overlapping. Okay, in this way, and these two sp hybrid orbitals, they will maintain linear distance, means they will come to opposite directions and they attain a linear shape with a bond angle 180 degrees. So BF2 molecule so formed has linear shape and the bond angle in this molecule is 180 degrees, because on the central atom beryllium only two orbitals are there. Each one is having electron pair. So these electron pairs will be repelled from each other and hence they will try to maintain maximum distance. In this way they come to opposite directions and the shape of this molecule is called linear and the bond angle is 180 degrees. And some other examples for this kind of molecules having sp hybridization are C2H2, which is also called with the name ethine, is also called acetylene. Acetylene or ethine it is called with molecular formula C2H2. And other molecules are HCN, which is called hydrogen cyanide. Other one CO2, which we know as carbon dioxide. In these all molecules, central atom undergoes sp hybridization before bond formation with the other atoms. So from this, let us see now sp hybridization in acetylene molecule, that is C2H2, which is chemically known as ethine. Let us see the sp hybridization in ethine molecule. In the formation of ethane molecule, both the carbon atoms undergo sp hybridization initially, having two unhybridized orbitals, also, that is 2px and 2py. We know carbon electron configuration as 1s2, 2s1, 2px1, 2py1, isn't it? Because in the excited state carbon it will jumps, it's one of the 2s electron into 2pz orbital. Instead of being 1s2, 2s2, 2p2, it becomes now in the excited state 1s2, 2s1, 2px1, 2py1, 2pz1. So in the formation of ethylene molecule, before bond formation with other atoms, carbon in itself, it undergoes sp hybridization, means one s orbital and one p orbital. These two will intermix each other. That means 2s orbital and 2px z orbital, they intermix each other and result in the formation of two sp hybridized orbitals. And the remaining two p orbitals, they are 2px and 2py, will be remain unhybridized. Pure orbitals will remain there. Okay, now each carbon is having two sp hybridized orbitals. See, this is one carbon. These pink loops represents sp hybridized orbitals of carbon. This is one sp hybridized orbital and this is one sp orbital. And for this carbon also, this is sp hybridized orbital. This is one more. Okay, now one sp hybridized orbital of one carbon overlaps with sp hybridized orbital of another carbon atom. See here, sp orbital of one carbon overlapping with the sp hybridized orbital of another carbon to form a sigma bond. Here one sigma bond is formed between two carbon atoms, while the other hybridized orbitals of each carbon atom overlaps exactly with the half-filled s orbital of hydrogen atoms, forming sigma bonds. See here, each carbon has two sp hybridized orbitals. One sp orbital of one carbon overlaps with the sp orbital of another carbon atom, resulting in the formation of one sigma bond here at the middle. And each carbon has now one more sp orbital on the other sides. This sp hybridized orbital of carbon overlaps with the s orbital of hydrogen atom. In the other side also, that carbon also will overlap its sp orbital with s orbital of hydrogen, results in the formation of one more sigma bond. So in this way, each carbon forming two sigma bonds, one with other carbon atom, one more sigma bond with hydrogen atom. So in that way they are formed. Now each of the two unhybridized p orbitals of both the carbon atoms overlaps sideways to form two pi bonds between the carbon atoms. Now we said there two p orbitals are unhybridized. Those we say 2px and 2py. For each carbon atom there are two p orbitals with the single electrons. Now after the formation of the sigma bonds between the carbon atoms, these p orbitals overlap sidewise. 2py orbital of one carbon overlaps with the 2py orbital of another carbon sidewise, results in the formation of this pi bond. And 2px orbital of another carbon overlaps with 2px orbital of another carbon and results in the formation of one more pi bond. In this way, between two carbon atoms, totally they are forming three covalent bonds. One is the sigma bond, which is formed by the hybridized orbitals, and the remaining two are pi bonds, which are formed by the unhybridized p orbitals sideways. So the triple bond between the two carbon atoms is made up of one sigma and two pi bonds. Okay. In this way, this molecule also acquires linear shape. See, linear shape, and the bond angle here it will be 180 degrees. Okay. This is about the formation of sp hybridization in ethane or C2H2 molecule. Next, let us see another kind of hybridization, that is sp2 hybridization. The intermixing of one s orbital and two p orbitals of an atom to form three equivalent sp2 hybrid orbitals is known as sp2 hybridization. Okay, one s orbital and two p orbitals, they intermix each other to form three equal energetic hybridized orbitals. This phenomenon is called sp2 hybridization, and these orbitals formed are called sp2 hybridized orbitals. These are each one representing one sp2 hybridized orbital. Okay, the three sp2 hybrid orbitals are directed towards the corners of an equilateral triangle with a bond angle with an angle 120 degrees. So these three sp2 hybrid orbitals will be shaped in the trigonal planar shape or in the corners of the equilateral triangle, and here the bond angle will be 120 degrees between each orbital. Now, each sp2 hybrid orbital has 33% s character and 66.66% p character. Okay, because there is one s orbital and two p orbitals involving in this. Okay. Now let us see example for the molecules having sp2 hybridization. Let us understand this by understanding. Let us see this with formation of BF3 molecule, boron trifluoride molecule formation. Let us see here. In this, the central atom is boron and its electronic configuration in its excited state is 1s2, 2s1, 2px1, 2py1. Actually, it is to be 1s2, 2s2, 2p1 in the ground state. But before bond formation, it undergoes excitation and one electron jumps from its 2s orbital to 2p orbital. That's why it becomes 1s2, 2s1, 2px1 and 2py1. So totally boron has 3 orbitals with the unpaired electrons in its outermost shell. Now see here 2s, 2px, 2py. These are the valence orbitals with unpaired electrons. Now these in the excited state boron atom, one 2s orbital and two p orbitals intermix to give three equivalent sp2 hybrid orbitals in this way. Okay, one s orbital, one 2s orbital and two p orbitals, they intermix each other to form three equal energetic sp2 hybrid orbitals. If you see the other one, fluorine, we know fluorine has one unpaired electron in its 2p z orbital. Now, these three sp2 hybrid orbitals of boron overlaps with two p z orbitals of three fluorine atoms in their axis to give three sigma bonds. In this way, boron trifluoride molecule is formed by the formation of three sigma bonds, which are formed by sp2p overlapping. sp2 orbital of boron overlaps with p orbital of fluorine, thus forming a sigma bond. Okay. So BF3 molecule so formed has trigonal planar structure. So three bonds will maintain equal distance from one to another in the space and results in the formation of trigonal planar structure. The bond angle in BF3 molecule is 120 degrees. And some other examples for the molecules having sp2 hybridization are C2H4, which we say commonly as ethylene. Chemical it is ethene or ethylene on BCl3 etc. In these molecules, the central atoms are undergone sp2 hybridization before bonding. Let us see the sp2 hybridization in ethylene or ethene molecule, that is C2H4. In the formation of ethene molecule, one of the sp2 hybrid orbitals of carbon atom overlaps exactly with the sp2 hybrid orbitals of another carbon atom to form carbon-carbon sigma bond. Okay, before sigma bond formation, each carbon undergone sp2 hybridization, means one s orbital, two p orbitals intermix each other in the formation of sp2 hybridized orbitals, and one orbital is remained unhybridized. These purple ones are hybridized orbitals. This blue colored hybridal representing unhybridized orbital. Now each carbon is with three hybridized orbitals and one unhybridized orbital. Now when these two carbon atoms approach each other, one sp2 hybridized orbital of carbon overlaps with sp2 hybridized orbital of another carbon in the formation of a sigma bond. And while the other two sp2 hybridized orbitals of carbon atoms, they are forming sigma bonds with s orbitals of hydrogens. See here, s orbital of hydrogen overlapped with sp2 orbital of carbon. Here one sigma bond is formed. Here one more sigma bond. Okay, in this way, each carbon is forming three sigma bonds. Out of those three, one with the other carbon atom, remaining two are with the hydrogen atoms. Okay, now there are two unhybridized orbitals, one on each carbon atom. In the unhybridized orbital of one carbon atom overlaps the sideways with the similar unhybridized orbital on the other carbon atom to form a pi bond, which is somewhat weaker than the sigma bond, which consists of two electron cloud distributed above and below the plane of carbon and hydrogen structure. See here, already sigma bond is formed. This blue colored one is representing unhybridized orbital of carbon. Now, these two unhybridized orbitals overlap sideways like this. After the formation of sigma bonds, these two unhybridized orbitals overlap sideways in the formation of a pi bond. Thus, two carbon atoms now they are having one sigma bond at the middle, which is formed by hybridized orbitals, and a pi bond which is sideways to the axis of their nuclei. Okay, in this way, C2H4 molecule is formed with the sp2 hybridized carbon atoms. Okay, let us see the remaining hybridizations in the next session. Thank you for watching our video. Please subscribe our YouTube channel AIMS Today and visit our website aimstoday.in for latest updates on recorded videos.